Hi, welcome back. Today we are going to be working on essential question 3, which will be going on page 127 in your interactive notebook. Today's focus will be comparing and contrasting the two confirmatory drug tests, which are spectrophotometry and mass spectrometry. So up to this point, we have looked at field testing, also known as presumptive testing. We now know that those are not going to be admissible in court due to the fact that they have a high incidence of false positives, which we saw in the Ed puzzle. We know that from that presumptive test that we can move on to gas chromatography, which is a separation technique. We'll discuss that today. And finally, we'll move on to either spectrophotometry or mass spectrometry. For your weekly agenda, you want to make sure you do today's check-in. Want to complete EQ3 with our essential questions, annotations, and our summary. Our two assignments for this week will be the textbook, pages 161 through 164, 1, 2, 5, 6, numbers 13, 14, and 16. And then lastly, you'll have a graph comparison chart that you will complete before moving on to the quiz on Friday. So let's get started. The first thing we want to look at is after you've completed your presumptive test, which might have included your microcrystalline test or your spot test, which we know there were quite a few. There were the Marquis, the Duquesnoy, Levine, just to name a few. And you have confirmed that you have a possibility of a presence of a narcotic or a controlled substance. You are going to move on to gas chromatography. So gas chromatography is an intermediate step. It does not allow for identification, but it is very important because it's going to allow us to separate our drug into its component pieces. So just like in liquid chromatography, where separation was our key output, we're going to look at two phases. So just like before, we're going to have a stationary phase, and we are going to have, so our stationary phase here. In our stationary phase before, that was our paper. And in gas chromatography, our stationary phase is going to be a viscous liquid. So if you're not familiar with the word viscous, perhaps maybe you forgot what it means or where it comes from. It comes from the word viscosity. And a viscosity is a liquid's ability to flow. So when we look at liquids that have high velocity, we are talking about liquids that are very sticky or they don't flow very well. For example, honey or molasses. We would say that those are highly viscous, so no flow. If a liquid is low viscosity, then we will say that it does flow very well. For example, water. So I always used to remember low flow. If it has low viscosity, it's going to flow very well. So we are going to want a high viscosity liquid that we're going to put into a column or into our gas chromatography apparatus. And that viscous liquid is going to allow the mobile phase to move through the column or the tube, very slowly though. And our mobile phase in this case is going to be a gas. Okay, and so we're going to look at the word here that's highlighted in yellow, and it says inert. So an inert gas is going to be a gas that lacks the ability to chemically react. So we do not want to create new mixtures. We want to just separate our current mixtures into their component parts, and the inert gas will allow us to do that. So very common gases that are used in gas chromatography are nitrogen or helium, and those are going to be placed into your apparatus. So the mobile phase will be forced through that stationary phase along with your testing substance, so your drug, your unknown drug, and it is going to allow you to separate into component parts. So let's move on to the analysis portion. When we analyze the graph that will be created, we're going to notice that we're going to have a series of peaks. So if we look over here at our graph, we're going to notice that this particular graph has peak 1, peak 2, peak 3, peak 4, and peak 5. And each of these peaks is going to represent a component, or for lack of a better descriptor, I'm going to say an ingredient. So this is going to be an ingredient or a component to your drug mixture. On the x-axis of your graph, you are going to notice that it says minutes. And so when we see that unit minutes, we often think of time. And that's exactly what we're talking about when we're talking about gas chromatography. So our x-axis is an indicator of the amount of time that it took for your components or your ingredients of your drug to pass through the column. So if we look at component 1 with this largest peak here, we see that component 1 passed through the column at approximately 1 minute and maybe 20 or maybe 30 seconds, depending on how you want to read that. But it came through that column between 1 and 2 minutes time. So it was the first thing to pass through that apparatus at approximately 1 minute and 20 seconds. Peak 2, significantly smaller than peak 1, came through right at 2 minutes. Peak 3 came closer to the 3-minute mark, maybe at 2 minutes and 40 seconds. Peak 4, just a little bit after 3 minutes. Peak 5 after 4, so in between 3 and 4, possibly at 3:40. And then we see that the components basically ran out. So we know that in this graph, we have 5 component ingredients to this particular mixture. On your y-axis, you're going to see here that it says signal, and this is going to represent the approximate concentration of each of these component parts. So again, the minutes is a direct reference to time at our x-axis. Signal is to concentration, and each of these peaks represents an ingredient or a component to your drug. Looking back then, we see peak that is proportional to the quantity of the substance present. So we see, if I were to ask you which of these components of the 5 has the largest quantity, you would be able to say, well, peak 1 has the largest or the tallest peak, so that would be your answer. And if I asked you which one was the lowest quantity or the least amount, you would come back and say peak 2. And just to kind of show a difference between retention factor, which was used in our paper chromatography or our thin layer chromatography, we see that instead of retention factor, we are now using retention time. And then again, that was noted here that each of these peaks appears at an approximate time. So let's move on to the next slide. So what is gas chromatography used for? So as I said before, gas chromatography is going to be used as a separation technique. We want to note that it is not considered a confirmation of a controlled substance. So this is not an admissible test in the court system for the very reason that it does not actually confirm, nor does it identify the identity of a substance. It merely separates, and it does allow us to see what concentration of each component is. But until that last test, that confirmation test is performed, we really don't know what those peaks represent. We use it as a separation tool prior to being used for mass spectroscopy, which is MS, or infrared spectroscopy, which is IR. So we're going to use our gas chromatography before we move into our mass spectroscopy or infrared spectroscopy. It does allow us to quantitatively measure the concentration of a sample. So we see that it's a quantitative measuring, kind of like you might use like a measuring cup to measure the quantity of something. You're going to use your gas chromatography to find relative quantities of different components to your drugs. But again, it does not identify what your drug is. So it simply separates that drug. So in a courtroom, there is no real requirement to knowing the concentration of a substance. It's not going to affect guilt or innocence. In particular, in sting operations, if a person believes that they are buying a certain drug, concentration is not going to play into that. If they believe that they are buying 1 kilo of drug, then that 1 kilo stands. As far as that amount is concerned, it doesn't necessarily have to be pure or not. It's the intent that we're looking at. What are the limitations to gas chromatography? So like I said many times before, gas chromatography simply cannot identify specific compounds. It does not have that capability. It is simply a separation technique. Now, why use it then? Well, the primary reason we use gas chromatography is mass spectrometry cannot separate mixtures. So your mass spectrometer is unable to separate mixtures. If you place, let's say, a Kool-Aid compound into your mass spectrometer, it would not know what to do with that information. So what it does need is it would need you to separate your Kool-Aid compound, your mixture, your cocaine, whatever it may be, into its component parts so that it can identify each part. That is where gas chromatography comes in. What about IR spectrophotometry? In IR spectrophotometry, it too cannot separate mixtures. So it is going to need that gas chromatography apparatus to separate your mixtures, and then each component mixture is placed into their various machines to get the identities. How do we fix these problems? So we know the limitations of gas chromatography is that it does not identify. We know that the limits of mass spectrometry is that it cannot separate. We know IR spectrophotometry cannot separate. How do we fix that problem? We combine them. So by combining gas chromatography with mass spectrometry or combining gas chromatography with IR spectrophotometry, we can solve our problem by first separating our mixtures and then identifying them. This is a very simplified diagram of what that may look like. So we see here that our first apparatus is a gas chromatograph. Your substance is going to be placed into the injector where it's going to be heated through the inlet. The column here shown as a coil is going to force that inert gas, as earlier mentioned, that could be nitrogen or helium, and that inert gas is going to cause your mixture to separate where it is going to lead to the detector. The detector is going to provide you with a graph that looked like this one. So now we have our 5 peaks, and each of these peaks, 5, 4, 3, 2, and 1, will be forced through the ion source, in this case in a mass spectrometer. Now we'll have, let's say, component 5 will go through the ion source, where it will be ionized or bombarded with electrons. It's going to be separated by mass, by its new charge, detected, and then we're going to have an identifying graph created. This graph, which we're going to talk about more in detail, will allow us to positively identify our unknown drug. So again, the limitations: one cannot identify, these two cannot separate. We put them together and we're able to separate and then identify. Each test is going to be run off 2 different principles. So in spectroscopy, okay, we're going to be looking at the interaction of electromagnetic radiation with matter. So the matter here is going to be referring to our drug. The radiation is going to be alluding to the energy waves that we're going to be sending through our drug to basically excite it into either transmitting or absorbing a certain wavelength. So the device that we used is called the spectrophotometer. This is an instrument that's going to use to measure and record our absorption of our spectrum of our chemical substance. So one thing we need to know is that spectrophotometers are going to be reading or charging our drug in the infrared, which is why it's IR. They're going to be using infrared wavelengths. So what you see here is a very simplified version of the electromagnetic spectrum. And let me turn off my focus there. And what we're going to notice is that your electromagnetic spectrum is divided up by wavelength, where we have very small waves, like our gamma rays and X-rays, ultraviolet rays like those from the sun, very small band here of visible rays. This is what we see or we know as the color spectrum. And then we have our larger waves to the right. And so our larger waves are going to include things like mid-range infrared, thermal infrared, which you may know as heat, microwaves, TV and radio waves being our largest waves. So our wavelengths then are going to go from smallest on our left side all the way to our largest on our right. The range that we're going to be looking at is slightly larger range, slightly larger than visible, so it would not be something you could see with your naked eye. But this thermal infrared is going to be what's going to excite our molecules into bending their chemical bonds. And in that bending, it's going to affect how they absorb or transmit light. So our spectrophotometer is based on the absorption or the transmittance of infrared light or infrared wavelengths. What does the device look like? So a spectrophotometer can look like a lot of things, but this is kind of a simple one that we actually have in our classroom. And so in order for you to have a spectrophotometer, you're going to need a radiation source. And your radiation source is going to be linked to a frequency selector. The frequency selector is going to be referencing that frequency that we talked about when we talked about the original electromagnetic spectrum. So like I said earlier, we're going to be looking for infrared wavelengths. So we're going to want to set it for wavelengths within that infrared range. We're going to have a place for our sample to hold, and usually that is a small test tube-like container called a cuvette, and that will be placed into our sample holder over here in that range. We're going to have a detector to convert the electromagnetic radiation into an electric signal that will create our graph, and it will record that graph and produce a signal that we can then read and identify using a set of known spectrophotometer readouts. Some of the ones that we can use ultraviolet, visible wavelengths, and infrared. And for drug identification, we're going to focus on that infrared. What do the graphs look like? A little crazy here. So with our infrared spectroscopy, we are again going to be looking at our electromagnetic spectrum. So over here, we will be looking at this range here. So we see this is your visible light. We see our microwaves, our mobile phones, radios. So we're going to be right here in this range. And just to kind of reference really quick, this electromagnetic spectrum is in reverse order with our smaller rays over here and our larger waves over there. So this is slightly, well, it is completely reversed of the other one. The wavelengths do not change. It's just reversed, whereas the other one was small to large. This one is showing you large to small. But again, we are still using infrared, which is just right outside that visible range. So the graphs that we are going to get, we're going to have two options here. So the infrared light is going to be compared before and after passing a transparent control sample. So our transparent control sample could be deionized water. And we want to make sure we have that control sample so that we know our device is working correctly. So we're going to use a clear sample that we'll place into our reader. It will produce a graph, and then we're going to use that just to make sure that we have some type of difference from our control. Now, once we've done our control, we're then going to move on to our unknown. So our unknown, in this case, we have two options. We have ethanol and we have caffeine. And you can have one of two graphs. Now, the two graphs that we're going to be focusing on for our class and for our test are going to be transmittance graphs. And so we see that it says transmittance here on the y-axis. And again, it says transmittance here on the y-axis. And what we're basically measuring is we are measuring the amount of that infrared radiation that passed through the sample. So if your sample, for example, is not clear, let's say it's brown or it's yellow or it's red, whatever, it is going to absorb some of that radiation and it's going to transmit or allow some of that radiation to pass through the sample. This particular readout is measuring the amount of that radiation that passed through the sample at different wavelengths. So we see then on our x-axis, we have our wave number. So these are our wavelengths. And so we were measuring between 4,000 to 500. So we're having basically what it does is it increases its radiation, or in this case, decreases its radiation at steady increments. And then it measures how much of that radiation pass through the sample at each wavelength. And it's going to create this graph. What's important to notice about these graphs is that they are like fingerprints. Every molecule or every mixture, well, not mixture, but every molecule is going to put out its own separate graph. And it is a reproducible graph that allows us to compare our unknowns to a set of known graphs. So like, for example, this one, ethanol. If I have a mystery liquid, maybe I'm a police officer and I find a mystery liquid in a car I pull over and I want to know what it is, I can take it into my lab, I can have them run it, and they'll come back and say, oh, you have ethanol, which would be the same alcohol in beer. Again, good old caffeine right here. Maybe someone says, college student says, hey, those are caffeine pills. They're not controlled substances. You take it to your lab, you run it. Caffeine will always run this particular graph. Okay, so again, what are we measuring? The amount of light or radiation that passes through the sample. Our x-axis has the wave number, where we see that we are decreasing wavelength at steadily increments, and we're measuring the amount of radiation that is transmitted at each wavelength as it decreases from 4,000 to 500 on this particular graph. What about mass spectrometry? So in mass spectrometry, we are going to be measuring something entirely different. Even though we're measuring something entirely different, we are still trying to make the same claim. What is the unknown drug? So they both have the same purpose, identifying unknown drugs, but they're going to do it in two entirely different ways. So while mass spectroscopy was using infrared radiation to excite our molecules into bending their molecular bonds and then either absorbing or transmitting radiation, mass spectrometry is going to work by breaking those molecules apart into ionized pieces. So what it's going to do is it's going to break apart our unknown drugs into various ionized pieces. Now, if you don't remember from your chemistry class what ionized meant, ionized simply means that it is a molecule or an atom that has an electric charge. In this case, it's going to have a positive charge as it loses electrons. Then it's going to take those ionized pieces and it's going to sort them by mass. So let's go ahead and look and see what that's going to look like for us. So our electron beam is going to be directed at our sample molecules in a vacuum chamber. So like before, we're going to, let's kind of refer back. We're going to separate here in our gas chromatogram. We're going to place our component into this ion source where it is going to be bombarded, just kind of imagine like a firing range, with electrons. Let's go back to this one. So we're going to put our sample here. We're going to take our electron beam source and we are just going to bombard that sample. And it's going to vaporize that sample, bombard it with electrons. And now what's going to happen is we are going to accelerate those ions through our chamber into this area here where they are going to be sorted magnetically. And we see that separation actually starting to take place here. So we started with one sample, and now we see that we have our component parts of that particular molecule, not exactly like chromatography, but it's going to break these into parts, not so much ingredients. But think of Legos. You might have one Legos, maybe like a Lego house or something that you've created with Legos, and now you're breaking those Legos apart. They're all still Legos, okay? So they came from that original part. And we're going to see that they are broken apart and they're going to be sorted by mass. And that detector then is going to create a graph like this. So we see this graph looks a lot different than our other graph from our mass spectroscopy. With our infrared spectroscopy, where we had a lot of these smooth, continuous curved lines, so we see a continuous line, not necessarily a linear line in any way, shape, or form, but it is continuous. So we see a lot of continuous lines here. Why is that? Because this is a continuous interaction with radiation. In mass spectra, we see that we have these discontinuous vertical lines. And the reason why we have this is each of these little lines is representative of those mass to charge ratio, those little pieces that have broken apart from our original compound. This particular one is aspirin. So we're going to have our electrons break apart our sample molecules into positive charge fragments. Very important that we know that. Positive charge fragments. Again, now that's why we're able to use our magnet here by creating that magnetic field. They will be sorted and collected according to their mass to charge ratio by an oscillating back and forth, in other words, electric or magnetic field. In this case, we're using magnetic. And then the detection output is this graph that we see here. Let's go ahead and enlarge that graph and see what it looks like. So our mass spectra, just like with our IR spectroscopy, where each of these graphs could create a fingerprint-like identification, mass spectra is doing the same thing. So it does it in a different way. Instead of registering the amount of radiation that's transmitting or being absorbed, we're simply going to break apart that aspirin, or breaking apart that acetaminophen into its variant component pieces that we see here. And we are sorting these pieces by mass to charge ratio. So we see over here that M over Z. Let's go ahead and highlight that. On our x-axis, we see M over Z. M standing for mass. Oops. And we see the Z, and that's referring to that mass to charge ratio. So when it's written like that, dividing, or that division mark, that's showing you that it's a ratio. So we have a mass to electric charge ratio. And we have those guys sorted here from 0 all the way to 240. In this particular case, this one has been blown up, 0 to 150. What's on our y-axis? And we see that we have our intensity. So our relative intensity is going to be recorded on that y-axis, and our mass to charge ratio is going to be recorded on our x-axis. Each of our peaks here are showing a portion of that original aspirin molecule that was broken apart. So we can see functional groups represented here, or different component parts that are represented here. But again, this particular graph is a fingerprint. So aspirin will always produce this basic 4-peak graph. And I'm just kind of referencing these 4 larger peaks, but this basic 4-peak graph that you'll be able to identify. So if you were given an unknown, you could go back to your log of all of your known drugs and simply match. Acetaminophen, aka Tylenol, also has a very separate set of peaks, also has a very separate set of functional groups in this molecule that we're going to be able to read out and identify. IR spectrophotometry and mass spectrometry. Both of these are going to work very well in identifying pure substances. So whether you choose IR spectrophotometry or mass spectrometry really just is a matter of what device does your department have, what device does your classroom have. In our case, we have IR spectrophotometry. So it just kind of depends on what device that your particular department went to use. But they both are going to work very well for identifying pure substances. Both of these devices cannot separate. So that is going to be one of their shortcomings, is they both are going to require a gas chromatography addition in order for them to analyze and identify your substance. So they're going to struggle with those mixtures. Both are going to be compared to a set of known drugs that are then housed in a catalog. So you can simply go to your catalog at the end of your textbook in one of your indices, and you can actually find the set of known drugs that you can compare your unknown drugs to. And we'll be doing that later this week as a practice. So in summation, what can we do? What do we know? gas chromatography is an essential part of both processes as it works to separate your mixtures into their component parts. Each of those component parts can then be placed into the IR spectrophotometer or the mass spectrometer. You do not need both. It's one or the other because both of them work well at identifying pure substances. And that brings us to the end of our essential questions for our drug unit. If you have any questions, please reach out to me in the comment section, or you can email me or find me on School Loop. Have a good day.